So when dealing with thermochemistry, we talk about internal energy, and internal energy is based on the heat and work of a system. So in this example here, we have a sample of water. It's placed in a freezer. It releases 8.75 kilojoules of heat and performs 2.35 kilojoules of work on the surroundings. What is the change in internal energy, delta E, of the system? Now, in this chapter especially, the sign matters, because if you have the right number but the wrong sign, it's incorrect. So make sure that always in all of these questions you have the right sign for the question, for the answer. So what we need to know about delta E is that delta E is the sum of the heat and work. And since we release 8.75 kilojoules of heat, that means the heat is leaving the system. Q is negative. Now with the work, we're doing work on the surroundings. And the only type of work that we're going to deal with in this, when we're talking about thermochemistry, is pressure volume work. And so pressure volume work means that we're at a constant pressure but changing volume. So if we do work on the surroundings, that means the volume of the system is going to expand. It's going to get bigger. And so if work equals negative P delta V, if delta V is positive, when we work on the surroundings, that means work must be negative. And so here, the work is negative 2.35. Again, because we're doing work on the surroundings, we're expanding our system. So if we're expanding our system, delta V gets bigger, means it's going to be positive. Therefore, work will be negative, because remember, work equals negative P delta V. And V is final minus initial. So when we expand, our final is greater than our initial. So now we just sum them up, and we get a negative 11.10 kilojoules. Now in this question, this is important because when we're talking about thermochemistry, we're talking about delta E, which is internal energy, and delta H, which is enthalpy or heat at constant pressure. So delta E can be related to delta H, but also includes work. And so for most chemical reactions, there's very little work done compared to the amount of heat released. So when we were looking here to see which one of these reactions would have the greatest difference between delta H and delta E. So what this means is that it's going to have the most amount of work done on this reaction. So the greater the work, the bigger the difference is going to be between delta H and delta E. The less the work, or if no work's done, the smaller the difference between delta H and delta E. And the most obvious question is, how do we know to determine the difference between delta H and delta E? And there are three types of reactions. So there are reactions that don't involve gases. So these are things like precipitation reactions, certain redox reactions. And so since they don't involve gases, delta V is approximately 0. So since delta V is approximately 0, the work is approximately 0. So therefore, delta H is approximately delta E. The second type of reactions are reactions in which the moles of gas doesn't change from reactant to products. And so if the moles of gas don't change between reactants and products, delta V is 0, then delta H equals delta E. Again, delta H is the heat at constant pressure. The last type of reactions are the ones in which the moles of gas do change. So here the work is not going to be equal to 0, but the amount of heat produced from the reaction is a lot greater than the amount of work performed by the reaction. So delta H and delta E are approximately the same. However, the more moles of gas that change, or I should say, the greater the change in the moles of gas, the more work that is done on the system. So when we go through each one of these reactions, we want to see, okay, are there gases present? If so, is there a change in the moles of gas? And which one has the greatest change? So we look at the first example, or the first A. So you see all the reactants and products are gases. So if we come here, we see on the reactant side, we have a total of 4 gases. On the product side, we have a total of 2 gases. And so the difference, which is always final minus initial. So delta N of gas equals 2 minus 4, -2. So we lose 2 moles of gas going from reactants to products. We look at the next reaction. So on the next reaction, we have everything's a gas. So we have 4 moles of gas on the reactant side, 7 moles of gas on the product side. And by the way, when your moles of gas are negative, what does that mean? That means that the system has contracted. So the final volume is less than the initial volume. So the system has contracted whenever the change in the gas moles is negative. And so here we have the change in the moles of gas equals final minus initial, we get 3. So in this example, the system expanded. In C, we see that the reactants, there are 2 moles of gas. On the product side, we have 2 moles of gas. So here, the change in the moles of gas is 0. So here, delta H would equal delta E, because there's no change in the moles of gas. If we look at the next one, we see now we have H2O liquid, and since it's a liquid, we don't include it when counting moles of gas. So on the reactant side, we have 1 mole of gas. On the product side, we have 3 moles of gas. So the change in the moles of gas is 3 minus 1. Which equals 2. And then in our last one, the solid, we don't include. So there's a solid on the reactants and product side. You see on the reactant side, we have 10 moles of gas. And on the product side, we have 0. So change in the moles of gas is 0 minus 10 is -10. So now you look to see which one had the greatest difference in the moles of gas. You see in this case it's E, so E would have the greatest difference between delta H and delta E. It still won't be much difference, but it'll have the greatest among all of these listed. And so C would be where delta H equals delta E. If it asked, the question could have asked which one is where delta H equals delta E. That's when the change in the moles of gas is 0. So in this thermochemistry, we deal with calorimetry, which is a way of measuring heat of a process or reaction. And there are 2 types, coffee cup and bomb calorimetry. So here we want to know what's the final temperature after 15.5 kilojoules is absorbed by 35 grams of water at 20 degrees Celsius, and it gives you the specific heat of water. Now bear in mind that sometimes it won't give you the specific heat of water. That's like a universal constant. So, you don't, on a test, of course, it'll be provided, but on the homework or quizzes, it may not be provided because that's a well-known constant. And so to calculate, or the equation we're going to need is Q equals mc delta T, because we have some mass of water, it absorbs some amount of energy at an initial temperature. And so to determine the final temperature, we know that delta T equals T final minus T initial. And we know T initial, but we don't know T final. So what we're going to have to do is solve for delta T so that we can solve for the final temperature. So the Q needs to be in joules, so we have to multiply by 1,000 to get it in joules, and of course we have the mass and the specific heat. Now we can solve for delta T. So we get delta T to be 105.8 degrees Celsius. We add this to T initial, we get the final temperature of 125.8 degrees Celsius. So that would be the final temperature of the water. Now this is a fairly straightforward calorimetry problem. And the next problem, a little bit more involved. So here we have a piece of metal, it weighs 59.047 grams. We heat it to 100 degrees Celsius. We put it in 100 milliliters of water, which has an initial temperature of 23.7 degrees Celsius. You allow some time, the metal and water come to an equilibrium temperature of 27.8 degrees Celsius. And the next sentence is, or the next part is very important. Assuming no heat is lost to the environment, calculate the specific heat of the metal. So that assuming no heat is lost to the environment is very important, because that assumes that no heat is lost or absorbed by the calorimeter. Because if heat is absorbed by the calorimeter, it's going to complicate the calculation. So here all the heat released by the metal is absorbed by the water. So again, to calculate specific heat, we need to know the heat of the metal, the mass of the metal, and the delta T. So we don't know the heat that was released by the metal. We know the mass of the metal. We want to find specific heat, and we know delta T, because again, it's T final minus T initial. So now to find the heat released by the metal, that's equal to the negative of the heat absorbed by the water. So we need to find Q water, then we can find Q metal. And with Q water, again, we're going to use mc delta T. So now we don't know the Q, but we know the mass, we know the specific heat, and we know delta T. And again, for this, they assume that the density of water is 1 gram per milliliter. So now we can solve for the Q of water. So we get 1715.4 joules. Then we can take the negative of this and we get the Q of metal. So now that we have the Q of metal, we can put it into the equation and solve for the specific heat. Notice that the two negative signs cancel out. And your specific heat should never be negative. Now in this example, we're dealing with rocket fuel hydrazine N2H4. A 1 gram sample is burned in a bomb calorimeter. The temperature of the calorimeter rises from 24.62 to 28.16 degrees Celsius. The heat capacity of the calorimeter is 5,860 joules per degree centigrade. Calculate the molar heat of combustion of hydrazine in kilojoules per mole. So whenever you see this molar heat of combustion, this is referred to as the delta H of combustion. And delta H of combustion equals the heat of the reaction divided by the moles of your reactant or product. So in this case, we're interested in the moles of the reactant hydrazine. So we need to find the Q of reaction and the moles. Well, for the moles, it gives us the mass of the sample and the formula, so we can find the moles pretty easily. But how do we find the Q of reaction? Well, the Q of reaction is equal to the negative Q of calorimeter. So we can find the heat absorbed by the calorimeter. We can determine the heat released by the reaction. And so Q of calorimeter is simply just the calorimeter constant, or the heat capacity of the calorimeter, times the delta T. And the change in temperature of the calorimeter is the same as the water that's inside the calorimeter. So we know the heat capacity of the calorimeter, we know delta T, we can find Q of calorimeter. Now again, I went ahead and converted it to kilojoules because it's going to want it in kilojoules per mole. Now that we know the Q of calorimeter, we take the negative of it and we get the Q of reaction. Next thing we need to do is find the moles of hydrazine. And so we take the mass divided by the molar mass, we get the moles of hydrazine. Now we can find delta H of combustion, and you see we get negative 663.8. And the negative sign is important because for heats of combustion, you're releasing energy. And in our last example, here we have a large paraffin candle, has a mass of 96.83 grams. A metal cup with 100 mils of water at 16.2 degrees Celsius absorbs the heat from the burning candle, increases its temperature to 35.7. Once the burning was finished, the temperature of the water was 35.7 and the paraffin had a mass of 96.14 grams. Determine the heat of combustion of paraffin in kilojoules per gram. Now notice it says kilojoules per gram. The other example was kilojoules per mole. And so again, delta H of combustion in this case is going to be the Q of the reaction divided by the mass of paraffin that was involved in the reaction. So again, Q of reaction is going to be negative Q of water. This is like a coffee cup calorimetry one. So we know if we know the Q of water, we can find the Q of reaction. And by the way, anytime you have a chemical reaction and you're looking for its delta H or Q, you're always going to measure it indirectly by measuring the heat absorbed by the water. So Q of water is simply MCAT, mass times specific heat times delta T. So we're looking for Q, we know the mass, we know the specific heat, we have the temperature change of the water, we can calculate Q of water. Now again, Q of reaction is the negative Q of water. So now we have Q of reaction, and again, I went ahead and converted it to kilojoules. There shouldn't be a decimal point here. And now, to find the mass of paraffin, we subtract the initial mass from the final mass. And this tells us how much paraffin was involved in the chemical reaction. Now we can solve for delta H of combustion, and we get about negative 11.82 kilojoules or negative 12 kilojoules per gram. So again, anytime you're looking for heat of combustion, heat of reaction, it's always going to be the Q of reaction divided by either the mass or the moles of a reactant or product.